Welcome to Pharma Drama, the channel where we look at the science of healthcare and healthcare products. Today we're going to look at two specific types of crystal forms, hydrates and solvates. We'll define what they are and look at how they can be useful, or not, in designing medicines. So, if that sounds good, get yourself something to hydrate yourself. I, as ever, have coffee, and let's make a start. Let's start with some basic definitions. I hope you remember that in a crystalline material, all the molecules are arranged in a repeating pattern, and that we define the arrangement of molecules that repeats with a unit cell. If we represent our molecule, which in the pharmaceutical world will be a drug substance, with a blue square, we might have a repeating pattern that looks like this. Where a substance can crystallise in more than one type of pattern, in other words, where it has more than one unit cell, we say it's polymorphic, and each form is a specific polymorph. We might represent different unit cells like this. If you need a refresher on that, there is a video on crystalline materials, the link for which is in the description below. Knowing whether a material is polymorphic is very important in the context of medicines because the physico-chemical properties of each polymorph, solubility, dissolution rate, bioavailability, and so on, will be different. Principally because the strength of the bonds between molecules in different unit cells will also be different. Closer packing usually means stronger bonds. We can use these differences to our advantage by tuning the performance of the medicine we make by selecting the most appropriate polymorph. Polymorphs can be ranked in order of thermodynamic stability. Usually, the more stable the polymorph, the greater the strength of the bonds, the lower the solubility. And this dichotomy is very important in drug formulation. We want medicines to be stable over long time periods, so the consumer can keep them for many years. But we also want them to deliver the drug as fast as possible. If the most stable polymorph has acceptable solubility, then that is the form that would be selected for development. But if the solubility is too low, then an improvement might be seen if a less stable polymorphic form is selected. Where there is only one type of molecule in the unit cell, then I consider these to be true polymorphs. However, it is possible that more than one type of compound may be present in the unit cell. We could represent that like this, with the light blue circle representing a second compound. These systems I call pseudopolymorphs, or polymorph-like. There are, as you might imagine, many types of molecule that might be present in a unit cell along with our drug substance. If the second molecule is water, then we have a hydrate. If it's a solvent, like ethanol or methanol, it's a solvate. And if it's a compound that is ordinarily a solid at room temperature and pressure, then it's a co-crystal. I was very careful with my last definition there. Co-crystals are an interesting type of system and have many uses in medicine design, but we will look at those in detail in a separate video. Here we are considering hydrates and solvates, and as I think you might imagine, from a pharmaceutical perspective, hydrates are much more important than solvates. Now, why might that be? It's because most solvents are rather toxic, so we wouldn't want to include them in our crystal form, because when that dissolves in the body, we would be dissolving both the drug substance, good, and the solvent, bad. However, I've defined them here so you know what they are. A pharmaceutical hydrate, therefore, is a crystalline form where there is both drug and water in the unit cell. Importantly, the ratio of water to drug must be stoichiometric. That means there must be a specific and exact ratio of water to drug molecules. If the ratio is 1:1, the substance is termed a monohydrate. If the ratio is 2 to 1, the substance is a dihydrate, and so on. Sometimes there may be more drug molecules than water molecules. Most commonly, there will be 2 drug molecules to every water molecule, and we call these systems hemihydrates. Whatever the ratio, a hydrate should be stoichiometric. If you measure the water content and the ratio is not stoichiometric, then we call the material wet. Normally, any extra water in a material has come from the way it was made, or by absorption of water from the environment. How would we determine if a material was a hydrate, simply a wet solid that was not a hydrate, or a wet hydrate? What would we do? We would use thermogravimetric analysis, which, I remind you, measures the mass of a sample as a function of temperature. As we heat a sample up, if water is present, it will evaporate, and we will see a loss in mass. Does water loss have to occur at 100 degrees centigrade? The answer is no, although that's a common mistake I see students make. Pure water boils at 100 degrees centigrade because that's the temperature at which the water molecules have enough energy to break the bonds holding them together as a liquid. But when water is bound to other molecules, not itself, the strength of the bond may be greater or lesser than that in liquid water, and so that will require more or less energy respectively to be broken, in which case we will see evaporation at higher or lower temperatures. Let's consider what we would see if we analyse different types of materials. If our sample was a pure polymorph, so no water in the unit cell, and was dry, we would see no mass loss as we heated it up. Well, unless the drug itself degraded on heating to form a gas, but let's not overcomplicate things. If the same sample was wet, we would see a loss in mass as the water evaporates, usually around 60 to 70 degrees centigrade, because surface water is not usually strongly bound to pharmaceutical materials. Because we know the mass of water, we can determine the stoichiometry, and we would find it is not stoichiometric. If we now heated a hydrate, we would also expect to see a loss in mass as we drive the water out of the unit cell. But now, when we calculate the ratios, we would find it is stoichiometric. This is one of the easiest ways to determine that a material is a hydrate. X-ray diffraction is, of course, another. The temperature at which water is lost from a hydrate can vary enormously, because the strength of the bonds between water and drug will also vary enormously. So we cannot know from the temperature at which water is lost that our sample is a hydrate. We have to rely on stoichiometry. And finally, in terms of analysis at least, what would we see in a TGA if our sample was a wet hydrate? I'll give you a moment to think about that. What would we see? We would see 2 distinct losses in mass, one corresponding to surface water and the other to water from the unit cell. Could we differentiate these based on the temperatures at which they are seen? Maybe. It's usually the case that surface water is lost first, but not always. So the best thing to do is calculate the stoichiometries. If you're wondering about solvates, they would do the same thing in a TGA. The only thing that's tricky is when you don't know what solvent might be present, because you need the molecular mass to calculate the ratios. In which case, you can examine the purge gas emitted from the TGA with a mass spectrometer. This type of experiment is called evolved gas analysis, or EGA. Are pharmaceutical hydrates better than anhydrate crystal forms? This should of course be the key question. And the answer depends on what we mean by better. Since everyone in the pharmaceutical world is obsessed by solubility and dissolution rate, then if the question is, does a hydrate form dissolve faster than the corresponding anhydrate form, the answer is likely to be disappointing. Usually, a hydrate form dissolves more slowly than a corresponding anhydrate. Students often find this surprising. After all, dissolution means breaking the bonds holding our molecules in a crystal lattice and forming new bonds with water. Surely, therefore, in a hydrate, this process has already started, so dissolution should be more rapid. I can see the logic of that argument, but in reality the rate of dissolution will come down to how strong the bonds are in a crystal lattice, and water has a propensity to form really strong bonds because it's an excellent hydrogen bonder. Remember that the water in a hydrate is not free water. Rather, the water molecules form an integral part of the unit cell. And if water-drug bonds are stronger than drug-drug bonds, which they usually are, then the hydrate will dissolve more slowly, and this of course reduces bioavailability. Let me give you an example. Here are the blood plasma versus time profiles for theophylline, as a hydrate and as the anhydrate. You can clearly see that the anhydrate form is more bioavailable because it dissolves faster. Why then do we care about hydrates? After all, what use are they if they are particularly useless in medicines? Well, that's a good question, and there are three main answers. Firstly, we have to know what the physical form of a drug is when we formulate it into a medicine. A hydrate is considered a different physical form than an anhydrate by the regulators, so we have to characterise and define what is in a product. Secondly, it may be the case that a drug which is formulated as an anhydrous, pure polymorph, can form a hydrate upon exposure to a humid environment. How might that happen, I hear you ask? Well, imagine that a patient keeps their medicines in a bathroom and they are keen on hot showers. Surprisingly, many medicines are stored in humid environments, and even the humidity in an average room will be around 65 to 75%. So it's really quite likely that a product will be exposed to humidity, and if a hydrate can form, it will. This is usually a bad thing because, as we just saw, hydrates have lower bioavailabilities. So if a hydrate forms on storage, the performance of the product may reduce. Therefore, drugs that have the propensity to form hydrates are often carefully packaged in blister packs that limit exposure to humidity, or are packaged with a desiccant. In fact, if you see a desiccant in a medicine package, it tells you that hydrate formation is a problem. Aripiprazole, marketed as Abilify, is a good example. If exposed to water, aripiprazole will convert to a hydrate, and the hydrate form dissolves really slowly. So Abilify tablets must only be taken from the blister pack right before administration. You might not think this is much of an issue, but actually patients taking multiple medications often put their daily tablets in a dose set box, and this mustn't be done for products that might form a hydrate. The third reason is because hydrate forms, by being slower dissolving, can actually be used to make long-acting dosage forms. If I pick aripiprazole again, I said that the hydrate form dissolves really slowly, so immediate release tablets must be shielded from humidity. But the hydrate form of aripiprazole is used in Abilify Maintainer, which is a long-acting product. In this case, the formulation is injected to form a depot under the skin. Because the drug is in a hydrate form, it dissolves really slowly. But in this case, that is what makes the product long-acting. A very clever use of physical form there, I hope you'll agree. So, there we are. Hydrates and solvates, although these are usually unusual in medicinal products, are pseudopolymorphs because they contain at least two types of compound in the unit cell. If the unit cell contains drug and water, we have a hydrate, and if the unit cell contains drug and solvent, we have a solvate. Hydrates usually dissolve more slowly than the corresponding anhydrous form because water typically forms strong bonds, and this has the effect of increasing the crystal lattice energy. Slower dissolution means lower bioavailability, so drugs with a high propensity for hydrate formation must be protected from humidity. In some cases, however, the fact that the hydrate form dissolves more slowly is actually used as an advantage to formulate long-acting products. I hope you found that useful. If you did, please hit the like button and consider subscribing. That really helps promote the channel. Otherwise, thank you so much for watching, and I'll see you again soon.